Hello Chem 1. Earlier in Unit 2 we talked about physical and chemical properties. Today in 2.9 we're going to talk more about how those chemical properties help us categorize different types of matter into groups. If we look here at this concept map, we can get a good idea of how matter is broken down. The first major categories would be pure substances that have a definite composition, and then mixtures which have an indefinite composition. And then within those pure substances, we have elements and compounds. And then within mixtures, we have heterogeneous and homogeneous. Today, we're basically going to walk through this graphic organizer and just move our way down and talk about the different groupings. First thing we're going to do is start on the pure substances side. The most pure of all substances would be elements. Elements are represented on the periodic table of elements, and they're always going to be represented by symbols. It's either going to be one capital letter or a capital letter followed by a lowercase letter. We're currently up to 118 elements. They are pure because they have a definite composition throughout, because every atom within an elemental sample would be the same. Most symbols for the elements make sense. They would be based on the English name. There are 10 of them that have names based in the Latin root. So for instance, lead, the Latin name for that is plumbum, and therefore the symbol is Pb. Sodium is natrium, and therefore the symbol is Na. You'll notice on this list of 10 that these are elements that have been known about since ancient times, and that's why their names typically come from the Latin root. There is one German-based, which is tungsten, and the wolfram is the German name, and therefore the symbol is a capital W. Elements aren't always standalone atoms. Sometimes we have what we call diatomic elements. The way to remember these is with the acronym Brinkelhoff, or we say like Professor Brinkelhoff. We will say the word Brinkelhoff probably like 1,000,000 times this year. It will get really important kind of as we get toward the end of the year. It'll be important that you know the 7 elements that make diatomic elements. So, H2N2O2, F2Cl2, Br2, and I2, and then Brinkelhoff just shows us, so Br is the bromine, I is the iodine, and so on. So if I say Brinkelhoff, or if I say that's Brinkelhoff, that means that's me telling you, hey, that's diatomic, and we need 2 of those atoms bonded together. We do this because that's the natural state that those elements are found in nature. We don't find just one oxygen atom in our atmosphere. We find O2, and that's how oxygen stabilizes in the elemental form. Another type of element would be something called an allotrope. An allotrope is when the same element can make different types of organizations or different types of structures. So for instance, carbon can form graphite, but it can also form diamond and other things called Buckminster fullerenes, which we won't get too far into. Oxygen can make O2 or ozone. So there are certain elements that can make different types of molecules only using that one element. Those are called allotropes. Here's just a slide that's actually showing you Brinkelhoff. You'll notice that all the Brinkelhoff elements are kind of located in the same place on the right side of the periodic table, and then hydrogen, which is top left of the periodic table, is also included. On the right side of this slide, you can see the different types of allotropes of carbon. Carbon actually has a lot of allotropes. So we have graphene, fullerenes, carbon nanotubes. All of those would be allotropes of carbon. So the one part of pure substances would be elements. They have a definite composition. If we start chemically bonding those elements together, that would form compounds. And because they're chemically bonded together in a set ratio, they would also have a definite composition and would be considered a pure substance. For instance, H2O is 2 hydrogens for every 1 oxygen. And if you have a sample of pure H2O, you can be certain, because of the chemical bonding, that you have a definite composition. One thing we pause and do here during compounds is talk about how to find an atomic mass or a formula weight of any molecule. The way we do this is we list the elements in a compound, we count how many of those atoms we have of each element, and then we find the mass of each element from the periodic table, and then basically we add them all up. So let's take a look at this. If we have ammonia, which is NH3, we have 1 nitrogen and 3 hydrogen. If we look on the periodic table, we would see that nitrogen has a mass of 14.01. We'd also see that hydrogen has a mass of 1.01. And there are 3 of them in this molecule, so we would multiply by 3. So all of my hydrogen would be 3.03, and then we'd add that to 14.01, and we would get a mass of 17.04. Typically speaking, we're only going to keep 3 sig figs here, so this would be 17.0. This next substance is called magnesium hydroxide. Magnesium has a mass of 24.3. Oxygen has a mass of 16.0, and there are 2 of them because this 2 applies to everything in the parentheses. So we have 2 oxygens. And then hydrogen, we have 2 of those as well, and they're each 1.01 times 2. So we get 2.02, we get 32.0, and we get 24.3. If we add those together, we get 58.32, and we'd keep 3 sig figs, meaning our answer would be 58.3. And that's how you do a formula mass for any molecule. So that completes elements and compounds, which are the pure substances, which will have a definite composition. Now we're moving on to mixtures. Mixtures are when you take 2 things and you just combine them physically. There's no chemical bond that takes place, they're just in the same space. So for instance, trail mix or a bag of M&Ms, those are mixed together. They're still separate entities. It's still like a yellow M&M. It's just with or mixed together with other M&Ms. Some mixtures almost appear like they would have a definite composition. We call these solutions, and they're homogeneous. Homogeneous means that they are uniformly distributed particles throughout some type of solvent. So a solute is what is dissolved, like salt or sugar, and solvent is typically what does the dissolving. A lot of times this is water. Water is typically known as the universal solvent. So Kool-Aid, salt water, lemonade, even like an alcohol solution that you'd get at your local pharmacy is a solution, and it's homogeneous. And so if you look at that solution, it appears that those particles are evenly distributed. Other types of homogeneous solutions would be alloys and amalgams. An alloy is when we take different types of metals because of their different properties and we heat them up, melt them down, and then the metals evenly distribute in solution, and then we re-solidify them and you get an alloy. So stainless steel, brass, bronze, those metals that you think of that aren't on the periodic table because they're combinations of elements on the periodic table, those would be examples of alloys. An amalgam is simply just an alloy that has mercury in it. We used to use amalgams for dental work before we got more synthetic materials that worked better and are a little more white and match the color of teeth. Amalgams are an alloy. It's a little easier to see that heterogeneous mixtures do not have a definite composition. They're non-uniform, and it's easy to see that they're non-uniform. The best examples of these are suspensions. Suspensions are when large particles are mixed into a liquid and they stay suspended for a short period of time. After it rains, mud in a river that'll settle out slowly would be a suspension. Italian dressing, that when you leave it in the fridge, the spices and herbs, they settle down. That would be a suspension. You can have a heterogeneous mixture that's not suspended, like lots of food like salads or pizza. Those are heterogeneous mixtures because it's not, those particles or the toppings or the things within the salad are not evenly distributed. Another type of heterogeneous mixture is called an emulsion. This is a special suspension that occurs when you have 2 liquids, and something special kind of has to happen in order for them to mix. Typically, in an emulsion, you have 2 things that are immiscible. Immiscible is when 2 liquids do not want to mix. Oil and water is the classic example. Miscible is when they will mix. So water and alcohol are actually miscible, and you can mix them together and they'll dissolve. So oil and water are typically 2 agents in cooking or in condiments that are often present. And so a lot of times we want those things, that oil and water, to mix together even though they're immiscible. So what we do is we add something like an emulsifying agent. Egg yolk is an emulsifying agent for oil and water. An emulsifying agent has a polar end and a non-polar end. And what it does is it allows a polar substance and a nonpolar substance then to mix together using the emulsifying agent. Mayonnaise, ranch dressing, paint are all examples of emulsions, things that shouldn't mix together very well and stay mixed together, but they do. Over time, if you let them set, they will separate. Paint separates over time, and mayo, if you leave it sit a long time, it would separate as well. This is simply a slide that's showing how the emulsifier, or the emulsifying agent, coats one of the substances so that it can be evenly distributed through the other substance. And this can happen kind of in either direction depending on what you have more of. In this case, it's oil and water. Another type of suspension that's kind of interesting is something that's thixotropic. Thixotropic substances are typically appear to be solid. When they're stirred or pressure is applied, they'll actually flow like a liquid. So if you think about ketchup, ketchup will flow, but as you put it on something, it actually like piles up on itself, almost like a solid. So it's kind of one of those substances that's kind of in between a liquid and solid, and it would be a suspension. That's why the water kind of sits on top of the ketchup sometimes. Another heterogeneous mixture is called a colloid. A colloid is when you have medium-sized particles that do not dissolve, but they also don't settle over time. Typically, we identify colloids based on how they respond to something called the Tyndall Effect, which we'll talk about here in a second. But examples of colloids would be milk, fog, or gelatin. Lots of gel-based things are colloids, and it's because they have medium-sized gel particles within that substance. The Tyndall Effect is when you shine a light through a colloid, and because the particles are medium size, they will bend or refract the light, and you would be able to see the beam travel through the colloid, like this. In a solution, particles are really, really small, and so as the beam of light travels through the solution, you don't see it. The particles aren't large enough to actually refract or bend the light. So sometimes you have two things and you're like, I'm not sure if this is a solution or a colloid. The beam of light, or the Tyndall effect, is a great way to identify which is which. Here's some examples of some things we just talked about. We got brass, which is a metal solution. It's homogeneous. It is therefore a mixture. We have pulp and orange juice, which would be heterogeneous, not because the pulp would settle out over time. That's a suspension. We have tea, which has really, really small particles, which would be a solution, just like this red liquid down here that would be identified as a solution. We have fruit salad and Fruit Loops. Those are uneven distributions. That would be heterogeneous mixtures. And then we have this chrome rim here. That would also be an alloy, which would be a homogeneous solution. So with any type of matter, we can tend to start categorizing them based on their properties and the different groupings that we've created. So the last part of this presentation is just talking about how we would separate these things. Sometimes it's beneficial to take something that's mixed together in a mixture and separating it into its different parts. There are typically 5 ways to do this. The first way is through filtration. We will do this, you have already done this in class. We use a filter paper and a funnel. You could do this with orange juice and pulp. The substance that comes through the filter paper is known as the filtrate. So typically the purified liquid. And then whatever you typically keep in the filter paper, that's typically thought of as the residue. A second thing you can do to separate mixtures is distillation. This is when you have 2 different substances with different boiling points. And as you heat something up, the first substance with the lower boiling point will boil off first, and therefore would be able to be separated from the substance with the higher boiling point. This right here would be something you see in organic chemistry. It is an organic chemistry apparatus. So what we have over here is salt water. So we know that the water has a lower boiling point. We add heat, the water boils and travels up, and as it cools down, it would condense into water vapor, and we'd get pure water over here. What's left in this original flask? Just salt. So we've separated the salt and water simply using this distillation apparatus. The third way is probably the easiest way, extraction. You can do this just by picking things out. Like when I have trail mix, I pick out the M&Ms. That's extraction. You could also do this if you had something magnetic. You could use magnets for extraction, which recycling plants often do. A fourth way would be crystallization. If you have a solution and you have a solute that's willing to crystallize, you could remove solvent, and over time that solute would begin to crystallize. Rock candy would probably be the best example of this. And the fifth way to separate mixtures is using something called chromatography. Most pigments are very, very small, and therefore they will travel through cloth or paper towel depending on their size. The smaller particles will travel farther. And so you can use something like a marker to put on a paper towel at the bottom, and then as it absorbs water, it will pull those pigments apart based on the size of the pigment. And that brings us back here to our graphic organizer. As you can see, we started off with pure substances, which are elements and compounds because they have a definite composition. And then we talked about mixtures, which don't have a definite composition because they are just physically mixed together and aren't bonded together in set ratios. Homogeneous mixtures are uniform, which is a solution, and then heterogeneous mixtures are not uniform, which would be suspensions and colloids. That's really all there is to types of matter, and those are the different categories. Good job today. Keep working hard. We will see you soon.